All right, so something else that we need to know and realize here is that an integral is really also referred to as an antiderivative. Derivative. You guys got to catch me on my spelling here. I told you. It's an antiderivative, and also what's referred to as an indefinite integral. Okay? Let me explain what this is here. We have definite integrals, which was what we had just described here, where I have different bounds, upper and lower limits, and we will come back to this in greater detail and show you how to actually utilize and calculate a definite integral. But conceptually, we still need a little understanding about how an integral and a derivative relate to each other. So let's just look at our position function here. Okay, so if I have position, let's see, with respect to time, this is a time here, and I have velocity, again, velocity with respect to time, and I have acceleration, where we have a function with respect to time. Now, we should know and understand now, if I want to take the derivative, so I'm going to differentiate, okay, and take the derivative from the position to the velocity function. If I want to then differentiate or take the derivative of the velocity function, it's going to give me the acceleration function. Well, the opposite is true as it relates to the antiderivative or the indefinite integral. So if I take an acceleration function and I integrate it, I get the velocity function. And if I integrate the velocity function, I will get the position function. So these can actually undo each other. They are inverse to each other. So derivative and integral are inverse to one another. Okay, so by being inverse to each other, mathematically, how would we say it? Let's just say we have a function, let's see, we have some function of x, right? So if I wanted to take the derivative of that, the way I could show that is f prime, right? This is also, another way of saying this. Well, let's just leave it as this for right now, f prime of x, okay? Well, if I take the integral of f prime of x, again, dx, okay, the integral of f prime of x with respect to x, basically. If I integrate this function along x, what I get is the original function. So, like I said over here, if I if I take the derivative of the position function, f prime of x, that gives me the velocity function. If I take the velocity function, f prime of x, and I integrate it along x, it's going to give me back to the position function. So they undo each other. They are inverse to each other. Another way of saying this, well, if I have a function that says I have some function f of x, and I want to integrate that with respect to x. So if I have an integral function here with respect to x, if I want to operate and take a derivative with respect to x of this integral function, take the derivative of an integral function, they undo each other, and what you get is that original function. Okay, so they are inverse to each other. Taking a derivative of an integral function just unlocks it. It's like taking the squaring a square root, or taking the square root of a square. 6 and 1/2 dozen the other. There's different ways of looking at this, but they are inverse to each other. All right. So taking a look here, indefinite integrals. Let's create a little chart here, where we will have, let's say, f of x, and over here we're going to have the integral of f of x along x. Okay. All right. So let's graphically look at a velocity function here first, because I think graphically, if we look at this, this might help us. If I have a velocity function with respect to time, and it is just, let's say this is 1, okay, and out to some time t, okay, it doesn't really matter what that time is. But if I want to integrate this function, first of all, right, this velocity function is just 1. It's always constant. Okay, so what could my potential position versus time graph look like? I'm running out of space here. Well, what would that look like? So if I want to integrate that, I need to know the area under this. Well, what would give me a velocity function? That would just be 1. Well, the slope of the line of a position versus time graph is my velocity function. I have a constant of velocity of equal to 1, which means I need to have a slope where this m is equal to 1. And right on here, m is equal to 1. Okay? Well, that makes sense. Okay? The problem is, though, is that I really don't know where this line is, because I could have a line that starts down here in the negative position and still has a slope of 1. I could have a line up here. All of these lines, doesn't really matter where, I don't know my starting position. These all could be accurately reflecting the fact that the rate at which I'm changing my position, which is my velocity, is 1 to 1. They all have the same slope. So when you're taking the integral of a function and going backwards here, there's a little bit of uncertainty when I haven't created any defined boundaries for this function. So let's look at this here then. Okay, so if my function, okay, this is going to be basically our velocity function, or any function, but let's just work at it as if it's our velocity function. If my velocity function is 1, what would this integral give us? What would this function be? Well, again, to go from here to here, let's say here, if I go from this way, from integral of f of x to there, that's really me taking the derivative. And to go from here to here, well, that is me taking the integral. They go back and forth with each other. So my f of x is 1, which is what is here. If I then take the integral of that, what taking the derivative, well, to get 1, I need to have x, right? And that makes sense. Like if I started here, what is this function? This function is y equals x. But like I said, this could be y equals x minus 3. or y equals x plus 5. It doesn't really matter. So there's some uncertainty here that I need to include a constant. Now, in math, okay, this uncertainty, I'm going to go off the page here, this uncertainty of this constant is what you're going to be calling this in math. But for our sakes, this uncertainty, so the uncertainty when you're taking the indefinite integral is really, for us in physics, the initial conditions. Right? When we talk about this, what is this constant here? Well, it's the initial starting position. If x, in this case, the x value is time is 0, then your starting position would be -3, or your starting position is 0. So there's some uncertainty here that when we're just going from a function to an indefinite integral where we haven't defined the bounds, there's uncertainty there. But for us, it's really the initial condition. But for right now, just understand that indefinite integrals, it introduces this uncertainty about the initial conditions. Now, often when we're doing experiments, these initial conditions are things that we know or can measure. So it's nothing to be concerned about. Just mathematically, when we're talking about taking an indefinite integral, that's what happens there. All right, so let's look at a couple other cases. What if my function is 0? Well, wouldn't that, again, just be 0? But don't forget, where's my starting point? There's still this level of uncertainty of some kind of constant out there, this initial conditions that occur. Okay? What if we had 3? So my function instead of 1 was 3. Well, what function, when I take the derivative of it, is going to give me 3? Well, that would be 3x. So if I take the derivative here, this is a way to check, to go from this side to that side, we're going to take the derivative. They kind of go back and forth with each other. So 3x, if I take the derivative of this function, it would give me 3. So that looks good, but I still need this constant. Well, in other words, let's just say any constant, we can call this, let's say b for right now. Okay, any constant b is going to, when we integrate that function, is going to be x. It's really, that's the slope, and we still have this unknown. Well, what if I actually want x in here? What do I need to take the derivative of to get x? Well, we really need to have a second order here, right? So if I take the derivative of this, I can get rid of one of the x's and I end up with x. The problem is that if I were to take the derivative of this, a 2 would come down here, and that would give me 2x. But I don't really want 2x. I just want x. So I'd have to have something here canceling out the 2 that would come down. So I get x squared over 2 plus c. Well, what about x squared? Well, again, I need the third order here, so x to the third. But again, I don't want a 3 here, so I have to divide by 3. And you can kind of see, don't forget our initial starting conditions unknown there. We have this pattern that's occurring here. Let me say, let's try, well, what if I wanted 5x? 5x. Well, I have the x squared, and I still need that 5 to be there, and I still need to divide by 2. So this constant really doesn't do anything, it just pushes through. Okay? So this 2 would come down, the 2's would cancel if I did the derivative, and so we can see this pattern here. So what we're really working here, guys, is what is called the power rule for integration. So on your equation sheet, I really want something that says, well, x to the nth power, okay, is going to give me x to the n plus 1 over n plus 1 plus c. So what does that look like for us in terms of our equation on our equation sheet? The integral of some variable x to the nth power with respect across x is going to be equal to 1 over n plus 1 times x to the n plus 1. And n in this case cannot be equal to -1 because we end up with 0 down here. So there's a special function with natural log that we'll get into separately, but for this power rule for integration right here, which is what we're going to be primarily using when we're calculating integrals, this is how it's done. Okay, x to the nth dividing by n plus 1 and taking x to the n plus 1 power. All right, one last thing here I want to show you as it relates. Let's drive this in terms of what does it look like for us in physics concepts. So let's talk about, we got physics language. Okay, so instead of f of x, we're going to say that we have a function with respect to time, and we're going to integrate that function with respect over time. So again, if we have 0, what we said is that it becomes 0 plus some c. Well, rather than this constant, we're just calling it c, I'm going to call this a as a variable. Okay. Now let's move this down over here. And so if I wanted to integrate that function, so a, well, what do I integrate that? Well, I'm integrating it with respect to time here. So at, so if I take the integral of this, t to the first power, this goes away, I'm left with a. But don't forget our uncertainty. Okay, so I have some kind of initial conditions. Well, rather than again c, I'm going to call this initial velocity. Now let's take this function, move it down here, integrate this one more time. Well, so a to the t, this is going to be a t squared, but we got to get rid of that 2. So we end up with a t squared divided by 2, right? This is the n. This order is 1, so add 1 to it, gives it 2, and divide by 2, and the constant just comes along for the ride here. Plus initial velocity times time. Don't forget, we still have this uncertainty that we have to deal with, so let's call this uncertainty as the initial position. Well, wait a second, you probably recognize it already. This is, let's rearrange this, initial position plus initial velocity times time plus 1/2 a t squared. This is the UAM position function that we just worked our way and derived backwards using the integral from a constant uniform acceleration. All right? All right, we'll pick this up as we look at definite integrals in a little bit more detail in another video.